Hello, welcome to another Science in Seconds video. Today we're talking about general relativity. Pretty amazing, epic, legendary discovery in the history of science by our boy, Mr. Albert Einstein. You know him, you love him. Our boy, Mr. General Relativity, as I like to call him. He discovered this theory in 1915 and is when he published his papers. He had been thinking about it for a long time, thinking about his science and his wonderful math. And he publishes this legendary idea in 1915 with a few papers, pumps it out in a science journal. Here you go. Everyone's like, what does this mean? This is crazy. What are you talking about, Einstein? You're insane. Turns out he was right. Our boy Arthur Eddington proves him right. And Mercury's orbit, they did some math on Mercury's orbit. So, we're going to dive in. What is general relativity? What does that mean? What is he talking about? Well, I like to think of the big G here, if we think of G as in gravity. It's really Einstein's theory of gravity. It's now been proven many times over mathematically, all this crazy stuff. It's a big G here. So if you think of gravity, this is basically Einstein's view of how gravity works. How does it work? According to Einstein, according to the universe. Well, we now know that everything in the universe has mass. Matter has mass. Everything. If you got matter, you got mass. We humans got mass, tacos got mass, this thing's got mass, things got mass. So anyway, all these crazy things have mass in them. Mass basically creates little ripples, or as you've probably seen before, it indents and creates little impressions on the fabric of space. So Einstein realized that gravity is like if you have like a marble, I've done this trick with students before, but if you have a marble, or you have other rocks and stuff like that, and you have this fabric, this mattress, this little piece of fabric, and it goes, and it bends down, and it droops. Well, that drooping causes a little ripple, and it causes, think of like a trampoline, or like a bed mattress, or anything like with fabric that bends and ripples like that. Creates little impressions, and that creates little cool dents in the fabric of space and the fabric of time. And so gravity is basically creating these little kind of impressions in this kind of fabric, and so that's a way to think about it. It's also good, oftentimes we see gravity is working like in a 2D representation, so sometimes we'll see it on a 2D plane, which just means it goes like up and down, and then left and right. But actually, I'll show you guys, it actually works 3D too. So everything with mass, it kind of bends and warps and twists things, and all this crazy stuff. So really the planets and the stars and all this crazy stuff out in the universe, if it's got mass, it's bending and warping things and twisting it all around in these crazy dimensions. Dimension the dice, if you will, from Yu-Gi-Oh! That's how it works, is it makes little ripples in space-time. Pretty crazy. So it's not pulling in, it's just that it affects space itself, and it does these little warping, twisting things. So anyway, there's something called the equivalence principle. What is the equivalence principle? Well, pretty amazing. Probably one of the greatest ideas anyone's ever had, ever. Pretty crazy. If you have a dude in a box, this guy is here in a box. He's like, hey, I'm a dude in a box. He's like, hey. So if you have this dude in a box, this was at Einstein's patent office. If you have a dude in a box, or in an elevator, or a rocket ship, whatever you want, and it's moving up, if this elevator is moving up, that he's going to feel a force going down. So he's going to feel the opposite force. So what he realized in this, if you have a box or elevator and there's no windows or anything, you're not going to have any idea outside that frame of reference. You will have no concept that you are actually moving up. You're just going to be feeling like you're being pulled down. So in fact, he thought about gravity as motion itself. He basically equated, it's called the equivalence principle for a reason, so it's equivalent to, we're going to put a little cool squiggly sign there. It's equivalent, so motion is equivalent to big G gravity. So basically what his amazing idea was that motion itself, like in an elevator or in a train, that any accelerated motion, if you're accelerating, if you're moving, it's going to feel like gravity. You're being pulled down. You're going to feel that force. We feel the force here on Earth. It's pulling us down. Feels like down. Not really down. So because special relativity had to do with motion, he realized, wait, this is the bridge. This is the bridge across which I can talk about gravity, because it's basically kind of like motion. we feel it like it's motion. It's actually not, at least we don't think so, but his big boy idea was that, oh, it really does feel like you're stuck in an elevator. We would have no concept. Maybe we are in an elevator and constantly moving up. We wouldn't know. So this allowed him to talk about the mathematics and his theory in a way like, oh, it's basically like motion, which his special relativity theory did. How about that? Mega genius, big brain idea right there. Epic, legendary. So anyway, I just want to throw that out there where he kind of, this very creative idea. I love how Einstein's mind worked. It was very creative. It was always pulling ideas from other things. It was always take a little bit from here, take a little bit from there, see what kind of soup you can come up with. Pretty epic, pretty amazing. The same principle from special relativity applies to general relativity. How about them apples? And when he first announced this idea, it's like a big, mega gangbusters idea. It's like, what is this general relativity? This doesn't make sense. This is crazy. This is madness, whatever. But a couple things were used to prove general relativity. So I wanted to share that with you guys there. This is really the time that Einstein becomes like a legend. Like, oh my gosh, who's this crazy physicist guy? He's got crazy hair and he looks cool and like he's a big weirdo and he likes slippers and stuff. I don't know. Another fun thing I think about gravity here is we always like to think of gravity as down. I like to bring it back to the equivalence principle here. Now it feels like we're going down, but actually what general relativity proves here, that gravity is not pulling us down. It's actually pulling us towards the center of mass. Because if we think of the Earth, everything is attracted towards the center of the Earth. So no one is ever upside down. No one is ever really down. We're all attracted towards the center of mass. And so because we're all attracted to the center of mass, I like to think about this as a positive quote. Nothing gets me down. It just centers me. So always feel centered. Whatever gives you center, whatever gives you stability and peace, that's important. So whatever centers you is how you should operate and think about gravity. So that's pretty cool there. Another important thing is, what is this space-time thing? Because we often think, back in the days of Isaac Fig Newton, space was considered nothing at all. Space was considered unimportant in everything. Space didn't really matter. It's like, space, oh, it's empty, whatever, who cares? The math works, whatever, it just pulls stuff towards it, that's it, it's kind of boring, bleh. But yeah, it's this cool thing about space and time as one. Cool visual that I saw on this other video when I was studying up on this. So you think of time, we like to think of time as kind of unaffected. So if you think of time as the arrow as we normally think about it. But if this is time right here, this is our idea of time. It's just this line, right? Time is unaffected, it just keeps going forward. But in fact, what was proven was time itself also bends and warps, just like space, same thing. Your clock actually changes based on mass. Check this out. Even though they travel the same distance, the exact same distance, this line, because it's bent and warped, is actually longer. So the same distance has been crossed, and yet time appears to travel slower for this person, or if they're looking at remember, space itself bends and warps, but so does time. And so if one person is affected in a mass field, so like the movie Interstellar talks about, it's pretty amazing, this is actually true. But if you're around a more massive object like a black hole, very massive, it's going to really pull on space and time a lot. And so its time is going to be dragged, and it's going to be like taking a long arc around it because it's being dragged. It's like, ugh. Thinking about time in this operation, that time is bent and warped and twisted just like space. Pretty crazy, pretty epic. Think about it, it's crazy. Watch Interstellar, amazing. It'll kind of explain that a little bit. So final point here, so talk a little bit about effect on time, about how it's a theory on gravity, and gravity is really the effect of mass on space and time, and how it warps things. Pretty amazing there. As well as gravity just does not match up with the quantum world, with the world of the very small. It works very well with the world of the very big, planets, galaxies, stars, universe. It works pretty well. Very well. But it does not work in the atomic world. Once you get to the subatomic particles, they start doing weirdo stuff and they're doing their own thing. And so maybe one day we'll develop a quantum gravity, a theory on quantum gravity. Maybe that's the future. So that just about does it all with general relativity. Probably one of the biggest big brain ideas of all time. It's probably one of the most, I think, just in terms of theories, probably just the most creative scientific and mathematical theory kind of all wrapped up into one. It's probably the most artistically creative as well as mathematically verified and observed scientific theories of all time. So it kind of like is this weird fusion of all these different ideas, and took a big brain like Einstein to figure it out. So thank you, Mr. General Relativity. We acknowledge and accept and thank you for your amazing mega genius ideas. So that's all for Science in Seconds today. Hope you guys stick around, and I'll see you next time in the future for more cool science segments. Here we go.